class. In this video, we're going to be looking at the line of best fit. The learning intention of this video is for us to develop an understanding of the line of best fit and for us to learn how to create an equation for the line of best fit so that we can make predictions. In all of the linear models that we've looked at so far, both the variables have a perfect linear relationship, which means if you're trying to plot the values for a particular data set, this will form a nice straight line, as you can see by the example on the left-hand side. However, many practical scenarios do not have a perfect linear relationship at all, but the data set can still be modeled by an approximate linear relationship, as you can see on the example on the right, and that particular line is what we refer to as the line of best fit. So we define the line of best fit as a straight line that best represents the data on a scatter plot, as you can see over here. Now, this particular line should be positioned such that it is close as possible to all the data points. So if I also draw a line of best fit, this is what my line of best fit is. Notice that when you're drawing a line of best fit, the rule of thumb is that you should have approximately the same number of data points that's found above and below the straight line. The reason why we use a line of best fit is so that it allows us to make predictions either by extrapolation or interpolation, and I'm going to go in a bit more detail as to what these two words mean later during the video. Based on your understanding, identify whether the following line of best fit is accurate for the data set shown below. If you answer this question correctly, then you should have answered that yes, this is an accurate line of best fit, because A, notice that you've got roughly the same number of data points found above the graph as you do below the graph, and B, if you were to draw a rough outline of all the values contained in the scatter plot, notice that the line of best fit kind of runs through the center of that. So this is a very good summary, or as a really good average of all the values in the scatter plot. The next thing that I want to be talking about is how do we find the equation of a line of best fit. I just want to emphasize that we find the equation so that it helps us to make predictions, okay? So what this means is if I knew what the equation was, I could answer the following questions for this particular data set. I could find out what is the weight of someone if I knew what their height was, or additionally, I could also find out what was their weight was if I already knew what their height is going to be. So I could answer these types of questions. By now, you should already know that the equation of a straight line should be represented in the slope-intercept form, which is y equals a plus bx, where a is your y-intercept and b is going to be your gradient. However, when everyone actually works out what is the equation for their very own line of best fit, please note that everyone's answer will slightly vary for their value of A as well as their value of B. The reason why everyone's values are going to be slightly different is because 1, each person may use different coordinates, and 2, each person may interpret the value for that particular coordinate very differently. So you might be a number off from each other, and as a result, everyone's equation is going to be slightly different. So I'm going to go through 2 examples of how to find the equation for the line of best fit. So the very first step is for us to choose 2 coordinates that are found on the line of best fit. Something that I want to emphasize is that the coordinates that you choose doesn't necessarily have to be part of the original data set at all. And sometimes you will need to actually eyeball what some of the values are. And because you're eyeballing the values, it can actually be quite subjective, meaning that what I interpret as a value may be different from what you interpret as a value. Fortunately, in this particular example over here, I can clearly see that I could use these 2 examples over here, and these 2 data points are actually part of the original data set. Now, I clearly know what the value of this data set is going to be. However, if you look at this data set over here, notice that in this particular case, it is quite ambiguous. We don't know whether that data point corresponds to a Y value of 17.5, 18, or even 18.5, okay? And because of that, that's why everyone's equation in the end is going to be slightly different. But that's okay as long as you've shown the correct working out. In this example over here, I've interpreted that value as 0,18 and then this value as 5,25. And after I've done step 1, I'll now calculate the gradient by labeling each coordinate as x1, y1, x2, y2. And now to find out the gradient, I'll just use the formula. So in this case, y2 being 25 minus 18 over 5 minus 0. So if you put this into the calculator, 7 divided by 5 is going to be equal to 1.4. So that's my gradient. Afterwards, I need to now find out what is my y-intercept, what is my a value. Now, when you're trying to find out the y-intercept, This can be really easy if the y-intercept is clearly given to you or shown to you, like in this example over here. But sometimes if the y-intercept is not actually shown or clear, you actually need to solve for it, okay? But in this case, since I know my a value is 18, I'm going to write a is equal to 18, and therefore the very last step is actually going to be writing down my equation now. Now, one thing I want to point out is that when you're writing the equation, because you've got the letters v and t, I've written my equation like this, and I'm just going to substitute my values of a and b in, so therefore this is going to be my final answer. Now, if you examine example 2 very closely, notice that this example is a bit different because the y-intercept is actually not clearly given to us, and that just means that we just need to do a bit more calculations to get to our final answer. Anywho, let's start with step number 1. So step 1 says identify 2 coordinates that are found on the straight line. And just to remember, it doesn't need to be part of the original data set. So if you look carefully as to what I'm about to do, I'm going to choose this coordinate over here, and notice that that wasn't part of the original data set. So that's a nice easy coordinate that I could be using for my calculations. And another value that I could be choosing is this value over here. One thing that I want to point out is that if you look very closely at that particular coordinate, it actually falls just right under the 70 mark. So that's why I've actually made this value slightly lower than that. After you've done this, what we need to do now is we need to actually calculate our gradient. So I want to label the coordinates as so, and then just put the numbers into the formula. So 69 minus 45 over 70 minus 50, put that into the calculator, and this should equal to 1.2. Afterwards, I'm going to now find out what is the y-intercept. So to find out the y-intercept, I'm going to substitute the gradient as well as one coordinate into this equation over here. So in this example, I'm going to choose the most smallest values. So in this case, I'm going to choose 50 and 45. So if I substitute the coordinate into the equation, 1.2 times 50 is equal to 60 in this case. And now I'm going to solve for a. So I'm going to subtract both sides by 60. And if you do that, then 45 minus 60 is going to be equal to negative 15. So that's going to be our value of our y-intercept. So now all I need to do now is just substitute the values back into the original equation. So therefore, this is going to be our final answer. I would now like you guys to have a go with answering this question. Give yourself 2 minutes and then we'll go through the answers together. So the first thing that you should be doing is labeling the coordinates as x1, y1, x2, y2 so you can calculate the gradient. So in this case over here, if you did this correctly, your gradient should be equal to 9. Afterwards, I'm going to find out what is my y-intercept. So what is my a value? To find out my a value, I need to substitute my gradient as well as one extra coordinate into the equation. In this case, I'm going to choose the most easiest one. So I'm going to choose 1, 20. So if you substitute this in, this is what your equation should now look like. 9 times 1 is simply 9. And now I'm just going to solve for a. So move the 9 to the other side by subtracting both sides by 9. And in doing so, 20 minus 9 is equal to 11. So that's our value of a y-intercept. And therefore, that's going to be the equation of the straight line. The last thing for us to cover is to learn how to predict using the equation of the line of best fit. When we're making a prediction, there are 2 methods for us to use. We could either make predictions using interpolation, or we can make predictions using extrapolation. Interpolation involves making an estimation of a value that lies between 2 known values within your original dataset. Let me use an example to show you what I mean by this. In the scatter plot below, this shows the measured temperature as well as the number of ice cream sales generated in those particular days. When we're trying to interpolate, what we're trying to do is we're trying to find out what is a value that lies in between our domain in this case over here. So if we wanted to find out what was the number of ice cream sales generated if the temperature is going to be 21 degrees, because 21 degrees lies between 12 and 25 degrees, which is what we've already covered, then this is going to be an example of interpolation. And by using the equation, we could actually find that the answer is going to be $480. Now, in contrast, extrapolation is the opposite process of this and involves estimating data points that lies outside of the domain or outside of the range. So again, if you look at this data set over here, this is the domain over here, and notice that in this particular example, they were interested in finding out what was the number of ice cream sales generated when the weather was 29 degrees Celsius. And in this case, because it's outside, this is going to be an example of extrapolation. I'd like to further add that when we're making estimations via extrapolation, this can be very inaccurate because what you're doing is you're assuming that there's going to be a definite linear relationship that lies within that range as well. Let me show you what I mean by this. So if you look at the example on the right hand side over here, what they've done is they've conducted data between the ranges of 0 to 2000, right? And if you're trying to make a prediction via extrapolation, so let's say you're trying to find out, what is the y value when the x value or the load is equal to 3000. What you're doing is you're assuming that these values over here, which lies outside of the original data set, maintains and follows this same linear trend. However, as you can see over here, if you were to actually conduct the test and collect the results, this actually has a non-linear relationship. So, and because there's a possibility of it following a non-linear relationship, that's the reason why this is inaccurate compared to interpolation. So I said, hence it assumes that the estimated value follows the same trend, which may not be true at all. Let's quickly go through some examples now. So in this example over here, we're going to use the equation to make predictions of the car's velocity. Now this example was the one that we actually covered earlier on. So that was the equation that we got earlier. So now I'm going to substitute 2.5 into the equation to find out what was the car's velocity at 2.5 seconds. So if you substitute it in, you're going to get an answer of 21.5 meters per second. Make sure that you include the units in your final answer, and you do the same thing for part B as well. And in doing so, your answer is going to be 27.8 meters per second. In this example over here, because it's asking for 2.5 seconds, that's going to be an example of interpolation, whereas for 7 seconds in this case, because it lies outside of the data set, this is an example of extrapolation. And for the final example, it's asking when will the car's velocity be equal to 30 meters per second. So what we'll do is we'll substitute v is equal to 30 into the original equation and solve for t. So what I'll do is I'll minus 18 from both sides of the equation. 30 minus 18 is equal to 12. And then I'll divide both sides by 1.4 to solve for t. And therefore your answer is going to be 8.6 seconds. To get further practice, I'd now like you guys to please answer questions from exercise 6G part 3. There's a total of 3 questions, so it shouldn't take you too long. This is the end of the video. Thank you guys for watching, and I'll see you guys again in the next one. Bye.